Good evening, everyone. I'm Jyoti Sharma, and this is week 9. The live session will be from 6 to 8 p.m. This is my brief introduction that right now I'm a PhD student from ISA Bhopal. I did my master's from FRI Dehradun, and undergraduation was from Delhi University. Right now, I'm a PMRF research fellow. That's why I have this teaching responsibility. I already have covered a few NPTEL courses, for example, air pollution and control, environmental chemistry and microbiology, basic environment engineering, and pollution abatement. So that's how I think such NPTEL experience will help me definitely to smoothly run this live session also. Okay, from week 1, right now this is week 9. So we from week 1 to week 9, we learned that in my slides I have multiple MCQs, and we try to solve this with the discussion. Uh, Whatever you are giving me wrong or right answer, because I'm here to correct you. Participation is highly valued. You will learn, I will also learn from you. So this is kind of win-win situation that we have if we are having the discussion. uh, yeah, so right now I have multiple select options. So uh, you can select more than one option, and that's how it will make a little difficult. And I think that will help you to understand concept in a better way. So that's how today I do not have just one option correct, but you may select multiple as the correct answer, right? This is just the brief recap that I want to give you. What we learned from week 1 to week 8 and how we are going. So, what is our direction? So, first we started with very basic environment thing. Different compartment we have in the environment. For example, we have soil, we have water, we have air, we have sediments. At each compartment we may have some chemical component. Let's say that chemical component is 1, and that chemical component may move among this compartment from air to water to sediment to soil. So uh, so that's how so we need to learn what are the physical and chemical properties that we have of this chemical component, the first thing. The second thing is how this compartment, how it is moving in the compartment, what is the tendency of that component A to move among the compartments. So that we learned in the week 1. Along with some parameters, we also learned about the water quality and the air quality parameter. For example, we learned about VOD, we learned about COD, and in air quality parameters, we learned uh, we have carbon monoxide, we have sulfur dioxide and nitrogen dioxide. So we talked about some parameters by which we can assess whether our water or air is pure or in the naive form or not, or it is altered or contaminated. So this we learned in week 1. But week 2, I think among this week 1 to week 8, the week 2 was very important because this is how your component or chemical will move from one compartment to the another compartment. And we learned about the partition coefficient. So either and this is dependent on the chemical property of your compartment and chemical properties of your component as well. So I already given you one example of the benzene. So benzene, let's say it is a organic, right? If it is a organic, then the compartment which have the organic component, so benzene will like that compartment. So the tendency of this benzene will be higher for the compartment that already have some organic component. So this is how we learned about partition constant, Henry constant. We learned about a lot of constant we learned, and this constant till like right now we will talk about week 9, right? But in week 9 also we are talking about the partition coefficient. So I think this is the base. The week 2 is the base for your whole course. So I think that you already have studied it nicely. Then we moved to week 3. So this was environmental monitoring and sampling, and in which we discussed about the quality, we discussed about the precision, we discussed about the accuracy. If you are having any test, then what is your confidence that whatever test you have done, um, that is correct or not. So we learned about these terminologies in week 3. In week 4 we started with the analysis, where if we want to extract the organic from the water, again I'm saying, let's say benzene or something, and if it is organic, then we have to extract it in the solvent. That solvent should be organic in nature. So we learned about this. So this was in week 4. In week 5, again we learned about organic load in water, but we started to learn about some techniques, for example chromatography and mass spectrometry. In chromatography we can separate chemicals, but in mass spectrometry we can try to identify what chemical it is. So we learned about this chromatography and mass spectrometry also. Then we started with the air and vapor monitoring method. So, for example, if you have air and within air you have some contaminant or some pollutant, then how you can monitor it? So, you first have to store air, either either in a natural form, or you can absorb using some solvent. So there were some method that we learned how we can extract whatever contaminant we have in the air to the test tube, and then how we can move it to chromatography or mass spectrometry to have the concentration. We learned about this. Then we moved to air, and in air we learned about the box model. Till now, we will use some concept of the box model, and it was nothing. What we are assuming is we do have a box, and the air is coming. Air may go out or not. There may be some reaction within the box. So this is something that we have some accumulation, and that accumulation should be equal to whatever coming in minus whatever is going out, plus what is there is a generation in that box, minus there is a decay. So this is how we learn. And within that equation, so this is a mass balance equation. Within that equation we learned uh, what do you mean by equilibrium. In the equilibrium there will be no accumulation, so we are putting accumulation is equal to 0. If there is conservative pollutant, so conservative means there is no reaction, so there is no decay, there is no generation, so where accumulation will be equal to flow in minus flow out. So such kind of cases we learned in the box model. We talked about the plume behavior, how plume will behave in different meteorological condition, and the most determining condition was the lapse rate. So how this lapse rate is different from environmental lapse rate. So this is adiabatic dry lapse rate is different from environmental lapse rate, and based on the rate we can determine what will be our plume behavior, and again the mixing height also. So we learned about this, right? Then in week 8, this was the last week. In week 8, we started with the dispersion model and Gaussian dispersion model. So this is something that whenever we have the plume, that plume is moving, but there is a highest concentration of the pollutant in the center, and that's how this is making a bell-shaped curve. And this is nothing but the Gaussian curve, or you can say the normal distribution. And from where we learned at what place there will be the high concentration of the pollutant, and at some distance we can calculate the pollutant. So this we learned in the week 8. Now coming to week 9, this is week 9. This is very important. And so this is something that you have air, you have water, in water you have, let's say, benzene. Okay, so this benzene will go to the air, but there are a lot of resistance. We will talk about those resistance, because there is the boundary, that you can say the interface boundary. You have air and water, in between that you have the boundary, and boundary will create some resistance. Okay, so we will talk about that resistance. And before resistance, we will talk about diffusion coefficient and the mass transfer coefficient. Okay, these are two very important coefficient what we will learn today in this live session. So I'm starting with okay, so I am just repeating that right now we don't have just one right answer, but we may have multiple so this is MSQ, multiple select options. So you can select more than one option as the right one, so that I think that will help you to understand in a better way. Okay, so I'm starting with first MCQ, not MCQ, but this is MSQ. Which of the following statement are correct regarding mass transfer driving force? Concentration gradient is always the true driving force. Chemical potential gradient is fundamental. Concentration is an approximation. At equilibrium, concentration must be equal in all phases. At equilibrium, chemical potential is equal across phases. So you have to tell me multiple correct answer, not just one, but there may be multiple correct answer. So this is something like, again, we will talk about that interface, right? So let's say, let me draw this. So let's say we have water here and we have gas here. And in water, we have some concentration uh, of A in water, and that concentration need to move this gas. So you have to tell me what are the driving force that can move this. Let's say this is the concentration of benzene. So what are the driving force that will move this benzene toward the gas? So let me see. I got B and D answer. Okay. So yeah, your answer is right one. And so, but before that, I have to make you people understand what you mean by this chemical potential and how this chemical potential is different from the concentration. Okay. So the first thing is, this chemical potential is different, is not equal to your concentration, right? Or you can say C, you can use. So this is not the same thing. uh, till now what we learned is that wherever there is a concentration gradient, then there should be the movement, but this is not correct. Even if we have same concentration, even then there may be some movement. So that is what we can say is that concentration is not important, but chemical potential gradient is. So first we will learn about this chemical potential gradient, and then we will move to the next question. Okay, let me first cancel the options that we have. So concentration gradient is always the true driving force, but what I'm saying, it is not the concentration gradient, but it should be the chemical potential gradient that is determining the true driving force. Concentration is just the approximate. We can have some idea where it should move, but it is not 100% that if there will be the chemical concentration gradient, then there will be the movement. No, this is just the approximate, right? So this one is not the right, this one is right. At equilibrium, concentration must be equal in all phases. No, till now what we learned is that equilibrium is when we do have equal concentration. No, this is not the right statement. The right statement is this is, let's say we have yeah, chemical potential. So if we have chemical potential is equal, or you can say we have flux, right? You have here water, you have gas, and if the flux is equal, or you can say the chemical potential is equal, then we can say there is the equilibrium. But uh, there is a equilibrium, so this one is the right answer, and D is the wrong answer, because concentration must be equal in all phases. No, at the equilibrium it is important to have equal chemical potential. But right now we are talking about this chemical potential gradient, so I think I should make you understand first what is this chemical potential gradient. So yeah, B and D one is the right one. Okay, coming to the formula for chemical potential gradient. So this is your chemical potential gradient or chemical potential. And this chemical potential is, this one is the change in your free energy. Change in your free energy when you are adding some number of moles. So for example, you have here, again I'm saying, you have water, and here you have, let's say, gas, and here you have benzene, right? And this benzene needs to move to the water. But before that, what we have to see is, in the gas, what is the free energy per mole? Free energy per mole. And you also have to calculate free energy per mole in the water as well. And based on this free energy per mole, there will always be there. If per energy per mole is equal to 0, then it means uh, you are in the equilibrium condition. But if there is any gap, so there is the chemical potential gradient, and there will be any movement. So this is something that the change in free energy when you are adding some substance. So, and mass will flow from high, this is your chemical potential. So high chemical potential to low chemical potential. And I think, yeah, so this is example that I put. So for example, in the container one, you have 1 mole and gives free energy is 10. So what you will do is you will calculate the chemical potential. So chemical potential will be 10 upon 1. This is equal to 10, right? In the container 2, if you have 10 moles, but your gives energy is 50, so chemical potential will be 50 by 10. That will be equal to 5. So it means your molecule will move from this container 1 to 2, because this one have a higher chemical potential as comparison to the container 2. So that's why this is important. Then, because we talked, there was one statement that concentration is just the approximation. So from where this concentration came into picture? So this is something that in ideal system we have this chemical potential. This is chemical potential initial, and you know, this is the ideal gas equation, right? So if we are having the gradient, chemical potential gradient, and so here also we have the gradient of the concentration. So what we can say, if there is a small variation, then this chemical potential gradient is proportional to the concentration gradient. But it is not same, it is not similar, but we can say this is just the approximation. So what we can say is, like, this is, let's say, diffusion. So diffusion is directly proportional to the concentration gradient. Okay, but it should be chemical potential gradient, but this is just the approximation. So it means there is a relationship between this chemical potential gradient and concentration gradient, but these are not equal to each other. Uh, so the right equation, most fundamental form that we should have is, this is your diffusion and this is your chemical potential. So there should be chemical potential, but if we are using here concentration gradient, then we are just removing these things and we are having very simpler form. So I think now it is very clear how concentration gradient is different from chemical potential gradient, and what is chemical potential gradient. So chemical potential is nothing but free energy per mole, and you will calculate free energy per mole in one medium and in the second medium, and then you will see which medium has the high chemical potential, and then it will move from high to low, and that will create a gradient, that is the chemical potential gradient. Okay, so this is how uh, so whenever we are moving anything from one phase to another phase or from one medium to another medium, then in place of concentration, chemical potential gradient is more important. I think I should skip this one. Yeah, here I just wanted to give you one example, that at interface. So again, I'm drawing the same thing. This is your interface. This is your water, and sorry, this is your gas, and there is some concentration of A that we have in the water, and we will move this concentration from here to here. So what you can say is that obviously the concentration here in this phase, this will be different from this place. So these are your boundaries, right? These are your thin boundary, and this is your gas and water. So what I can say is that uh, uh, because we do have very two different phase, so two different phase, it is very near to impossible that we will have the same concentration. Okay, to maintain the equilibrium, the potential, chemical potential should be same, and concentration here will follow the Henry law. For the equilibrium, we should not have this concentration in water should will not be equal to the concentration in air. Okay, coming to the next question. Again, I'm saying we have multiple select um, options. So if you have species A in 1D steady state and you have this equation, I will tell you what that equation means. You have to tell me which statement is correct. If JA exists, even if Vx is equal to 0, if delta rho A by delta X is equal to 0, then J is equal to 0. Na is equal to 0 implies no transport. Bulk and diffusive flux can oppose each other. Don't worry, I will tell you each and every term, and what statements should be right and what statements should be wrong. So don't worry about this. I will make everything clear. So let me tell you, this Na is nothing but this is flux. This is flux. Flux is determined by two things. The first thing is flux is determined by two things. Along with A, there are other options that you have to click on. Okay, just tell me one thing. When there is a transfer or when there is the flux, okay, flux is dependent on two things. The one is you can say bulk moment, and the second is you have diffusion. So what I'm saying is that whenever you are moving, let's say you are moving something from water to air, there are two terms that will determine this movement. The first is bulk movement. Bulk movement means whenever you have any velocity, or if you have any flow rate. For example, a river is moving. Okay, along with that river, uh, a contaminant or pollutant A can move. Okay, so if we do have any velocity or if we have any flow rate, then pollutant will move from one place to the another place. So this is nothing but this is the bulk movement. Okay, the second is diffusion. So diffusion is whenever you have chemical potential, whenever you have chemical potential among these two phases, then there will be movement. Okay, and here we do not require the velocity or the flow rate. Okay, so it means for the movement we need two terms, the bulk movement and the movement by the diffusion. So this is your flux, this is your bulk movement term, this is your bulk movement term, and this is your diffusion term, right? Okay, now we need to tell which statement are correct. Now, one thing that you have to understand, we always have the diffusion. We will always have the diffusion. Why there will be the diffusion? Because uh, uh, because we have chemical potential that will exist, and because of that, and there is a second law, that is the entropy. Okay, so this is something that let's say I'm giving you one example. If you have water here, if you have water and if you are adding sugar in it, okay, if you are adding sugar in it and you are not steering it, so if you are not steering it, it means you are not giving the velocity. Okay, so this means this bulk movement will be zero. There will no any transfer of this sugar into water due to the bulk movement, because we are not steering it. But still there will be some sugar will be dissolved in the water. So why is this the case? Because this is the diffusion. Diffusion will always happen. Diffusion can't be zero. Okay, so it means okay, now coming to the statement, this is your diffusion. Diffusion exists even if Vx is equal to zero, if velocity is zero. Okay, I'm taking that example. I have water, and in water I'm adding the sugar and I'm not moving it. My water is very stagnant. Okay, I'm not moving it, velocity is zero, but there may be some transfer just because of the diffusion. So this is the correct statement. We can have the diffusion. J is nothing but J is the diffusion. So we will have the diffusion even if our velocity is zero. So this one is the correct option. Coming to the next one, so this is your concentration gradient, right? D rho A. So this rho A is a concentration with the distance. So this is your concentration gradient. If your concentration gradient is zero, then your diffusion will be zero. As I told you, diffusion is not dependent on the concentration gradient, but it is dependent on the chemical potential. Okay, and the second thing is there will always be chemical potential gradient because of the entropy case. We will learn about this, the second law of thermodynamics. But just keep in the mind there will be chemical potential gradient, and uh, so diffusion is not dependent on the concentration. Diffusion depend on the chemical potential. So this one is the wrong statement, right? Okay, third term, this Na, that is the flux, is equal to zero implies no transport. As I told you, diffusion will always give you the transport, will always give you the movement. So if Na is equal to zero, it means there was some movement, but that has been cancelled out. Okay, so This is again not the right answer, because if n is equal to 0, it means there was a movement, but that movement has been cancelled out. This is so okay. The bulk movement, we also known as this bulk movement as advection also, if you know this. So advection can cancel out the diffusion. There may be some case, you can tell me the example also. So if they are cancelling out, we are not saying that there is a no transport, but they are cancelling out. So bulk and diffusive flux can oppose each other. Yeah, this can be conditioned. Let me give you one example. If river is moving water in that way, so your concentration of some pollutant is also moving in that direction, but it may be that chemical potential is high here and low here, so diffusion will move in this direction. So it means due to advection, due to bulk movement, the direction is in the left hand side, but due to your chemical potential, the diffusion may be in right hand side. So they may be cancel out. And that's how uh, you may have you may have net flux is equal to 0, but it doesn't mean that there is a no transport, right? There was a transport, but it has been cancelled out. So based on that, okay, let me see this one. uh, I gave you B is also wrong, but here what I'm saying is that, okay, why this is B is the correct one, because in one slide, let me show you that one slide also. Yeah, so this is your diffusion, and here what we learned is that diffusion term should be like this. Diffusion is directly proportional to your chemical gradient, right? But what we also learned is that we can do the approximate, and that approximate is saying that your diffusion is directly proportional to your concentration gradient. So in that question, so in the next question also, what you will learn is that your Ja term, that is the diffusion. So diffusion is dependent on your diffusion coefficient, that is D, and then dC by dx. So this is your diffusion term. Okay, your concentration gradient. Okay, so what we are saying is that it should be your chemical potential, it should be your chemical potential, but we are approximating this chemical potential with your concentration gradient in the Fick's law. Fick's law is the simpler form, right? This is just the approximation. So in the Fick's law, what we can say is that your diffusion is directly proportional to your concentration gradient. So if it will be 0, then diffusion will also be 0. Then yeah, based on this equation, we can say, but in real situation it is not, but because concentration is not driving, chemical potential is driving, but Fick's law having the concentration term, not the chemical potential term. So that's why B is the right one. I think you understood what I want to say. Okay, I wanted to give you example where your advection or wind based movement can cancel out your diffusion. So first is evaporation with the wind. So there may be the case that wind is carrying the vapor and it is moving the vapor away from the surface, but there may be some concentration gradient. Based on that concentration gradient, there may be diffusion near to the surface, so that's how it can cancel out advection and the diffusion. The second is the groundwater contamination. there is some velocity in the groundwater, not too much, but there is the velocity, and based on that velocity, your chemical can move in that direction. But it may be that you have concentration gradient in the opposite direction, and diffusion can happen in the backward way. So these are the two examples that we have, that is showing that advection and diffusion can be opposite to each other. And based on that, we also have some numerical. Okay, now coming to the next question. So this D is your diffusion coefficient. This D is diffusion coefficient. This is your concentration gradient, and you need to calculate diffusion flux. So this diffusion flux is nothing but this is JA. So what is the JA? If you know the formula of diffusion flux, then this is very easy to calculate. And here we will have just one right answer, right? Because it is numerical and one answer will only be right. Okay, so again, I'm coming to the Fick's law. Yeah, A answer is the right one, because what we learned in the Fick's law is this is the Fick's law. Fick's law is all about the diffusion, and it gave us the equation for the diffusion flux, and this diffusion flux is nothing Ja. So this Ja is equal to diffusion coefficient and dc by dx, concentration gradient. Whenever you have any concentration gradient, and based on your diffusion coefficient is dependent on a lot of properties that we will talk later. But yeah, so there should be simple multiplication that will give you the flux diffusion. So if we are multiplying this 200 to 3, so this will give us the 600, and uh, 600, and then multiply by 10 raised to power minus 9. And yeah, so that's how it will give me let me show you the solution, how it is giving. Yeah, so very simple. This is just you have to multiply, and that's how you will get the answer. In spite of 600, what we are having 10 raised to power 9, we are reducing it to 10 raised to power 7, because we are removing two zeros from 600. Okay, now we have Ohm's law has a similarity with the Fick's law. Okay, and you have to tell me which are the correct. Flux is directly proportional to gradient. Resistance is directly proportional to dx by d. Large D means larger resistance. Gradient acts as driving force. Which answers are the right one? So the Fick's law have some similarity with Ohm's law, right? And can you tell me what was the Ohm's law? What is the formula for the Ohm's law? Yeah. So Ohm's law is V is equal to IR, and I means I is equal to V by R. This is your potential difference. Okay. This is your potential difference, and this is your resistance. Now, what we learned is that we have JA, and this JA is equal, this is Along with, we have multiple right answers. So you have this is your this is your diffusion coefficient, then dc by dx, right? So what we are saying is, if this so we can also write this dA is equal to, sorry, JA is equal to dc dx divided by d, right? So this is your concentration difference, just like this one. This is your concentration difference, and your resistance is equal to dx upon d. So this is how we can have. So for the driving force, what we need is the concentration gradient and divide by the resistance. Okay, so for the moment, for the diffusion, so J is your diffusion flux, right? This is your driving force. This driving force is dependent on your concentration gradient, just like potential difference that we have in the Ohm's law, and also depend on the resistance. And if we will have less resistance, means there will be more diffusion. Okay, and this resistance is depending on the thickness of the boundary and divide by the diffusion coefficient. So because diffusion coefficient is reciprocal, it means whenever we will have more diffusion coefficient, we will have more diffusion. Okay, so now coming to what we may have. So flux is directly proportional to the concentration. This is your flux. JA is directly proportional to DC, right? So this is right, concentration gradient. So yes, my flux is directly proportional to the gradient. Resistance is directly proportional to dx upon d. Yeah, we compare it with the Ohm's law, and what we learned is that this term dx upon d is similar to our resistance term. So yeah, this is also right one. Larger d, this is the d is the diffusion coefficient. Larger d means larger resistance. No, this is not the right answer, because here what we are seeing, that this d will come in the multiplication of the dc. So this is your d, so this d is directly proportional to your flux. So what we can say is that whenever we have more diffusion coefficient, it means we will have less resistance. So this is the wrong statement. Okay, because resistance is dx upon d, and d is at the denominator. So that's how there is less resistance whenever we have larger d. Then gradient act as the driving force. Yes, it is. So our driving force is gradient and resistance is dx upon d. So this is how we are having the similarity. So what we learned is, right answer is A, B and D, not C. Okay, I already have given some, yeah. So this is what we already have learned. So this is your concentration upon dx. So this is your distance, this is your diffusion coefficient, and we also have learned about the Ohm's law. So this is I, this is the potential difference, and this is resistance. So resistance is, this one is dx upon d. So what we can say is the flux is equal to driving force and divide by the resistance. Yeah. Next question is, for a volatile compound between air and water, we have four options: equal concentration at equilibrium, equal chemical potential, continuous flux at equilibrium, partitioning governed by thermodynamics. Again, this is MSQ. So if a volatile compound is moving between air and water, then what are the conditions that are the right? uh, B and C. B1 is right. I agree with B that uh, equal chemical potential can equilibrium, but I'm not agreeing with the C, because if there is the equilibrium, then there will no any moment. Equilibrium means like there is a no continuous flux. And the partitioning is governed by the thermodynamics. This is obviously a very normal and general term. But the thing is, in equilibrium, your flux is denoted by this Na. This flux is zero. Okay. Because there is this no any accumulation, and that's how we are keeping this flux is equal to zero. We will learn about this in mass coefficient and all, but just keep in mind that whenever we are in, in equilibrium, then flux will equal to zero. There will no any flux, right? So that's how B and D is the right answer. So let me show you again. You already have learned that it is not the concentration gradient, but it is the chemical gradient that matters for this equilibrium. Because in two phases, if we have air and water, concentration will never be equal to each other, because we are following the Henry law, right? So this is the concentration of water is equal to Henry coefficient multiplied by concentration of the air, concentration of any component in the air. So that's why what we can say is that because our H is equal to not is H not equal to 1, that's why if we are talking about two phases, right, water and air, then concentration, it is near to impossible that the concentration will be equal. The equal thing can be the chemical gradient. So this is chemical gradient air is equal to chemical, sorry, potential of the air. Then we can say this is at the equilibrium. Yeah, and n is equal to 0, so there is a no net flux. So that's why that C answer was not the right one. Yeah, coming to the next one. Velocity is given, that is 0.02 meter per second. The density is also given, 1.5 kg per meter cube. Ja is your diffusion flux. The diffusion flux is also given, that is minus 0.01 kg per meter square second, and you need to calculate the total flux. What is the total flux? Okay, the first thing that we need to learn the unit of the flux. What is the unit of the flux? I think based on that, it is very easy. Unit of the flux is mass per area per time. Right, so can you see here kg per meter square per second? So this is mass per area multiplied by time. So this is your flux. Okay, so flux, this we already have learned, right? The rate, mass rate in mass balance, but in the flux we are dividing it with the area also to calculate the flux. So diffusion flux, so net or total flux is equal to the flux due to velocity, so this is the advection, plus the flux due to diffusion, right? The flux due to advection is velocity multiplied by your density. Just see here the unit, meter per second, kg per meter cube. So here this will cut and this will be 2, and that's how this will again give you kg per meter square multiply by second, the same unit. So you have to multiply, and then j is given, and then you have to do the addition, and that's how this will give you the right answer. So this is something 0.02 multiplied by 1.5. So we know that 15 multiplied by 2 is 30. And then minus 0.01. And that's how this will give me the answer. So let me calculate this. So this is your 30. Right, but here just check the decimal. So this decimal are 1 2 3, 1 2 3. So here we will have decimal, and then we are having the plus, and then we have minus 0.01. Right, so yeah, so what you can say is A is also right, right, and D is also right. Yeah, so either A or D, both can be right one. So right now I'm just clicking on A. So but both are same, right? 0.03 minus 0.01. That will give me the value 0.02. Okay, which statements are correct? Diffusion increase with temperature. Diffusion decrease with viscosity. Diffusion increase with molecular size. Diffusion higher in gas than liquid. Which statement are correct? Okay. So what we learned is diffusion flux, right? Diffusion flux is equal to diffusion coefficient, then dc upon dx. So this diffusion coefficient, this is the function of temperature, this is the function of viscosity, this is the function of molecular size, and a lot. So now you have to tell me how diffusion can change based on this particular variables or parameters. If we will have high temperature, then diffusion will increase. So I'm just giving you the example that if you have so let's say if you have in within air, you have carbon monoxide and you have nitrogen dioxide. So if we are increasing the temperature will help us steering it and help us to mix fast. So diffusion will increase with the temperature. This one is the right one. Diffusion decrease with the viscosity. This is also right. Viscosity is now let me give you one example. So for example, if you have one is sugar syrup, okay, and second is water. So sugar syrup has the higher viscosity as comparison to the water. So diffusion will happen more in water as comparison to the sugar syrup. So whenever we have high viscosity, then mixing diffusion will be slower and low as comparison to the any substance that have a low viscosity, right? So yes, diffusion will decrease with the viscosity. This is also the right option. Whenever you have any high concentrated substance that have the high viscosity, it means the diffusion will happen at very slow pace. So B is again the right one. Diffusion increase with the molecular size. This is a little difficult, that I will explain. I think later I have one MCQ question on this basis. And then we have diffusion higher in gas than liquid. Yeah, this is right. If you want to diffuse anything into the air, that is easier as comparison to the liquid. Okay, because we have molecular space that we have in the gas, and gas can give the permission to move this substance between these molecules very easily. So D is also right. A, B, D. Now coming to the C1, this C1 is not the right one, because whenever we will have heavier component or that have the high molecular size, the diffusion will decrease, that will not increase. And I think one function that I will give you in I think in the next MCQ or all, but you need to understand that molecular size will decrease the diffusion. So yeah, coming to the next question, why does diffusion occur spontaneously? We have four options. System seek minimum concentration, system seek maximum entropy, system seek maximum pressure, system seek uniform velocity. Again, I'm giving you one example of the diffusion. Again, we have water, and let's say we have here sugar. We are doing nothing, we are just keeping it. With the time, what we will learn that some sugar will be dissolved in water. So it means it is happening spontaneously, it is happening automatically, right? So why diffusion is happening automatically? Yeah, B answer is the right one, because system seeks maximum entropy. But again, the question is, what do you mean by entropy? What do you mean by entropy? You're right, that our system seeks maximum entropy. But what is this maximum entropy? Entropy is something, degree of freedom that we have. This is something DOF, I can say. Degree of freedom I have. So this is something that let me give you the example that our supervisor gave. So this is something that if we have urban area, and that urban area have high population density, then person will go to some place that have lower population density, so that the person can move around. If the density is very high, then person will not move. So this is also in the molecule also need a high degree of freedom. So to maintain that high degree of freedom, it will move, it will always move. So in the sugar, here in the sugar, it is uniform, the degree of freedom is very less, so it will move into the water to increase the entropy. Okay, and this is universal in the chemical world, that system always seek to have the maximum entropy, maximum degree of freedom. And that's how diffusion will happen spontaneously. And that's why I told that diffusion can't be zero. Diffusion will happen in any way just due to the entropy. So yeah, B answer is the right one. So what I can say is that system naturally evolve toward more probable state, and mixing can happen without any external forces because entropy increases. So coming to this again, in what condition there will be maximum entropy? When we will encounter the maximum entropy? Maximum entropy will be, so I'm giving you two hint. Either it will be more in stable. What do you mean by stable? Stable state always have low entropy, but equilibrium will have maximum entropy. So for example, we have water, right? We have water, and we are not adding anything into this. It is stable, it has low entropy. But if we are adding something, and then there will be some disturbances, some noise that will happen, and that will increase the entropy till there is an equilibrium. Okay, so a maximum entropy you will get whenever you will have the equilibrium condition. Yeah. So okay, near a solid surface, you have four options. You have to tell me the right answers. Velocity is zero at surface. Diffusion dominate transport. Turbulence dominates at wall. Gradient is highest near wall. So for the solid, let's say I'm taking the example of soil. So you have soil, right? Or and then you have to tell me what are different conditions that will happen near to the solid surface. Or you can also draw it perpendicular. So let's say this is soil and this is your air. So near to the solid surface, what will happen? Diffusion dominate transport. Yeah, I agree. But why? Why diffusion will dominate the transport? And that's how I think you can select more option. Uh, because you need to investigate why diffusion is dominating the transport, why it is not anything else. Velocity is zero at surface. This is also right. Yeah, because there is solid is giving you the highest resistance. Okay, and that's how this will reduce the velocity. So yeah, A is also right one. And coming about the turbulence, turbulence is opposite to the diffusion. Turbulence is always mostly due to the velocity. So because you already have given that diffusion is dominating, then turbulence is not the right answer. Coming to the gradient, gradient is highest near wall. Is that wrong or right? This is again right answer. Gradient will always be highest near the wall, because above the wall there is uniformity in the velocity, uniformity in the concentration, but near to the wall there will always be the gradient. So that's how D answer is also right one, and A, B, D are the right answer. Okay. So dx is given, that is 2 multiplied by 10 raised to power minus 3. D is also given, that is 2 raised to power 2 multiplied by 10 raised to power minus 9. You need to calculate the resistance. We saw the similarity of Ohm's law with the diffusion, net diffusion, and from where we learned the resistance. Yeah, A is the right answer. Then what we learned is that we have diffusion flux. Diffusion flux is equal to, this is your diffusion coefficient, dc upon dx, And then we make the similarity. What we learned is that dc upon dx divide by d, we call it as the resistance, right? So here we will divide these two, this will be cancel out, this will go above, so this will be 10 raised to power minus 3 minus minus 9, so this will be 10 raised to power 6. So yeah, A answer is the right one. Okay. Now coming to different compartment that we have in the environment, and different compartment, the net flux is dependent on, as I told you, we have two terms, advection term and the diffusion term, and in different compartment, different term will dominate. So you have to tell me the correct one. So I have A, river, advection dominate, groundwater, diffusion only, sediment, diffusion dominant, atmosphere, no diffusion. Again, MSQ, multiple select. We have different compartment, and in different compartment, what kind of movement that we have, or the mass transfer. So let me give you, in the river, this is the river, river is flowing, right? River is the flowing with always with the velocity, right? So will the transfer of mass due to velocity is always higher than transfer of mass due to diffusion. Okay, what it means is that it doesn't matter what is the value of diffusion that we have in the river, because most of this mass transfer is happening with the moving water, or the water that have the velocity, because it will move the substance from one place to the another place. Okay, so A is the right one, because in the river, advection, due to the velocity, the mass transfer will happen. Diffusion is kind of negligible, we can neglect it. Coming to the groundwater, what happened in the groundwater? Here you have, this is your unsaturated part, and this is your saturated part, and this saturated part is giving you the groundwater, right? Or you can say the aquifer. So what happened in the groundwater? Is there any moment, so is there any velocity with which the groundwater is moving? B for unsaturated. Yeah, you're right. Whenever we are having unsaturated, then diffusion will happen. But if we do have groundwater is saturated one, and because at there is always some velocity, that velocity is no doubt very low. But if you have learnt about the Darcy law, if you have learnt about this Darcy law, then Darcy law is saying that we have velocity of the groundwater that is proportional to your hydraulic gradient. So it means groundwater have some velocity, it means groundwater have some advection also, but that velocity is not high, is not too much high, and diffusion is also not too much high. So it means the groundwater is governed by both advection and diffusion. But if we are saying that groundwater is just due to diffusion, no, this is the wrong answer, because groundwater have some velocity, and whenever we are having some velocity, then most of, so there is high chance that advection will dominate. Okay, so this one is not the right answer, because it should be unsaturated one. Coming to the sea, sediment, diffusion dominant. Yeah, you're right. In the sediment, this is unsaturated condition, right? If there is any unsaturated condition, that uh, it means that we will, so this is something that if you have this soil particle, and on top of this you have, let's say, water, right? So if your soil particle have some contaminant A, and if it is moving to, let's say, water, it doesn't have any velocity, so there is no any advection. So whatever will happen, it is mostly due to the diffusion. Okay, so C answer is the right one. Coming to the atmosphere, in the atmosphere we have both advection and diffusion. We have wind, we have wind in the atmosphere. So whenever there is a wind, then there will be advection that will dominate. But sometime we also have some stagnant condition when wind is not moving, when we just have air, because wind is the moving air, right? So if we do have very stagnant or still air, it means your mass transfer is not due to advection, but it is due to diffusion. And in atmosphere we have both thing, we have advection, we also have diffusion. But here it is saying that in atmosphere we do not have any diffusion. No, we have diffusion. So this is the wrong answer. So A and C should be the right one. A and C. Okay, when this total flux will become zero, gradient zero, velocity zero, diffusion cancel advection, concentration zero. As I told you, total flux is determined by, yeah, C answer is the right one. So total flux is determined by the advection and by diffusion. And there will always be diffusion, right? So even if velocity is zero, velocity is giving you the advection term, there may be some diffusion, and that's how the net flux will not be equal to zero. Uh, Gradient is zero, but velocity can also zero. So that's how it, this total flux will anytime if it will be the zero, it means advection is cancelling out the diffusion one. Okay, if we have bulk flow that is opposite to the diffusion, what will be the net flux? If bulk flow is opposite to the diffusion, what will be your net flux? No. uh, Net flux is nothing but your bulk flow plus your diffusion flux, right? So 5 plus minus 7, is it? Your net flux is equal to the sum of bulk flow plus diffusion flux, right? So it should be minus 2, is it? This negative sign is itself is showing you where it is moving. So that's why A is the right one. Okay. Coming to the next question, which statements are correct? Stirring increase diffusion coefficient. Stirring enhance bulk transport. Diffusion exists without stirring. And mixing is same as diffusion. Okay, again, I'm having this sugar and water. So you have this water, and here you have sugar. Here you have sugar. So whenever we are stirring it, so let's say we are stirring it with some stirrer or spoon. If we are stirring it, then what will happen? Obviously, the sugar will be dissolved. Sugar will dissolve whenever we are stirring it. But stirring is doing what? Okay, coming to the first option, stirring increase diffusion coefficient. No, stirring is not increasing diffusion coefficient. Stirring means you are giving the velocity. If you are moving it or steering it, it means you are giving the velocity. And velocity is all about the bulk transport. Steering is not about the diffusion coefficient until or unless this steering uh, until or unless because we know that we have diffusion coefficient, and this diffusion coefficient is the function of temperature, uh, molecular weight, or viscosity, right? We learned about this, that we have diffusion coefficient, that is the function of temperature or molecular weight or viscosity. In case stirring is increasing the temperature, then I can say that this will affect my diffusion coefficient. But most of the time we are not keeping this as it is. So because this temperature increment due to stirring is the secondary effect, not the primary one. Due to steering, there is always increase in the velocity. So what I can say is this steering will increase my bulk transport. Okay, without, so this is right one, right? B is right one because steering will enhance my bulk transport. Coming to C, diffusion exists without steering. As I told you, there is always entropy. We have to maximize the entropy, and there will always be the diffusion. Even if you are not steering, still there will be some sugar that will be dissolved in the water. So this is also the right one. Mixing is same as diffusion, is it? No, mixing is a little different from the diffusion, right? So what do you think? What should be the right answer for this? So these are just B and C, right? Steering is all about increasing the velocity, and that's how, if we are increasing the velocity, then we are increasing the bulk transport. Okay, which mechanism dominate in sediments? Molecular diffusion, advection, bioturbation effect, turbulent mixing. In the sediment, what mechanism can lead to the mass transfer? Molecular diffusion, yeah, I agree with this. What about B, C, and D? This one is the right one. Obviously, sediment have the unsaturated condition, does not have the velocity, then molecular diffusion will help us to transfer the mass. What about the advection? Because we are talking about there is a no velocity, then there will be no advection. So this is one is the wrong one. What about bioturbation effect? If sediment have some microorganism, and that microorganism are having some activities, and because of that activities there are some mass transfer that can happen. I give you the example in the next slide. I think I have a few example about this. uh, Bioturbation, I will explain in next slide only. And then turbulent mixing is based on the velocity, so this is again the wrong one. So the right one is A and C, but because you asked me what is this bioturbation, let me explain this. So yeah, bioturbation is mixing and disturbance of the soil or sediment by the living organism. So how it can disturb or it can mix, so that mixing will help the mass transport, right? So how microorganism can help it? For example, it is borrowing, creating the channel. It is ingest or excrete the sediment, and that's how it is relocating the particle. It is taking it, it is moving, and then it is extracting it. So this means the movement is happening, but due to the microorganism. Okay. So there is the vertical mixing due to this bioturbation, and there also the redistribution of particles and chemicals. So these worms, burrowing animals, microfauna, this can help to mix and to transport one particle from one place to the another place. So there is the mass transfer, but due to the microorganism. So this is bioturbation. Okay. Flux increases when gradient increases, diffusion coefficient decreases, distance increases, temperature decreases. Okay, again, the flux is due to your bulk movement and due to your diffusion flux, right? And now coming to in the diffusion, in so this is let me clear this. So this is your net flux. That net flux is your bulk flow, and due to bulk flow and due to your diffusion flux. This diffusion flux is directly is equal to, this is diffusion coefficient, dc by dt, dc by dx, and this bulk flow is depend on velocity multiplied by concentration, right? So um coming to the question, gradient increase. So obviously, if this will increase, this is your dc, dc upon dx. So obviously, if your gradient will increase, then your flux will increase. A is the right answer. Coming to the second, diffusion coefficient decrease. Diffusion coefficient is also giving the directly proportional to your net flux. Diffusion coefficient, if it is higher, then your net flux will be higher. So this one is the wrong one. Distance, this is your distance, right? Dx. So when you are increasing the distance, it means you are decreasing the flux. This one is the wrong one. Temperature, whenever we have high temperature, that high temperature will increase the diffusion coefficient, and that will increase the net flux. So but here this is temperature decrement, so this is again the wrong one. So yeah, A answer is the right one. Okay, if we have C1, that is 5, C2 is equal to 1, dx is equal to 2, can you calculate the gradient? Very easy. You told B. Is it B? Yeah. So yeah, it is A, because we have this fixed law. It's saying that this is minus D, and then we have dc upon dx, right? And that's how this is giving you the -2, right? or you can say, like you can also go with this concentration. So this is how this will give you the -2. Okay, if we are coming to the diffusion coefficient, and which one will have the higher diffusion coefficient for the same compound? Gas diffusion in the gas, the diffusion coefficient is more as comparison to the liquid. Liquid more than gas, same magnitude, depend on the temperature. We are talking about the diffusion coefficient. So in which condition the diffusion coefficient will be higher for the same compound? Yeah, A answer is the right one, because diffusion is always higher in the gas as comparison to the liquid. So this one is the right. Not same magnitude. This one is the opposite. Depend only on temperature. No, it can depend on temperature. But if you are saying that it is only on temperature, then this is the wrong one. So A is the right answer. Chemical potential depend on concentration, temperature, pressure, all of the above. Yeah. So D answer is the right one, that your chemical potential is dependent on a lot of variables, and it is from ideal gas equation, right? So the D one is the right answer. Yeah, little tricky question. If you have diffusion time scale, this diffusion time scale is directly proportional to L, L square, 1 by L, independent of L. L is the thickness of your boundary or interface, you can say. A little tricky one because it need partial derivatives. So that's why I don't expect you to give me answer the right one. B answer is the right one, that is the L square, and let me tell you why. So this is something that changing the concentration with time. This is if we are having the second derivative. So this is the condition that we have. And if we are making similar this partial derivatives with this del C upon T, and yeah, then from here we can have this, and if we are extracting this one, so from here actually, so C and C will cancel out, so this will give me 1 by T, that is similar to D by L square. So it means your T is similar to or directly proportional to L square upon D, and this was asked in the question. A little derivatives you have to like you have to consider, you have to see. Okay, very important concept, that is the Packlet number. If Packlet number is more than 1, what does it imply? You have 4 options: diffusion dominates, advection dominates, both negligible, reaction dominates. I will tell you what is this Packlet number if you do not know. But if it is more than 1, then what does it mean? So the Packlet number is the ratio. Yeah. So Packlet number is the ratio of your advection term divided by your diffusion term. Okay. So if your diffusion term value is so if your Packlet number is more than 1, it means your diffusion was higher as sorry, your advection was higher as comparison to your diffusion. If your Packlet number is less than 1, it means your advection was uh, the mass transfer due to advection was lower as comparison to the mass transfer due to the diffusion. Okay, so that's how you can tell. So if this is more than one, then it means advection will dominate. For example, in the river we have advection that is dominating as comparison to the diffusion one. So yeah, same like this. Okay, just you just need to see the formula of this, because a lot of question can ask from this formula. So we have advection term, that is the velocity, and this is your concentration gradient. Your diffusion term, you have diffusion coefficient, and this is your concentration gradient. And then whenever we are doing the scaling and we are calculating the ratio, then this will be velocity multiplied by thickness divide by your diffusion coefficient, and that will be known as your Peclet number. Yeah, already. Okay, which are correct? Light compounds evaporate, heavy compounds sink, no diffusion occurs, dissolution possible. Dissolution possible, sorry. So if we are talking about this light component, uh, take the example of helium, take the example of nitrogen, take the example of any chemical that have very light, that are very light component. Most of the time they can evaporate. Okay, because yeah, heavy compound sink. Yeah, right. Heavy compound may sink. So this question is related to actually the groundwater. So in the groundwater we may have some light compound, we may have some high heavy compound. So if we have this is, let's say, your water table, and this is your groundwater, and if we will have some compound that will be leached down up to this groundwater, if this will be the light compound, then this compound can evaporate, and this can also move up. But if this is the heavy, then it can sink. It can sink, let's say, here. No diffusion occur. As I told you, there will always be diffusion. So this is the wrong one. Dissolution may also be possible, right? So A, B, and D are the right answer. Okay, what is the unit of flux? From slide 1 to till now, we are talking about the flux. So what is the unit of the flux? What is the unit of flux? Unit of flux is, I think you can calculate from the flux. Yeah, B answer is the right answer. We talked about flux, right? The flux is, here we have advection term and the diffusion term, right? We have diffusion term, and I told you this one, advection term is velocity multiplied by concentration. Velocity is meter per second, and this is your concentration term. Concentration is kg per volume, right? So this will cancel out, and this will give me meter square. So this is kg per meter square second. And if this term is has the unit this one, and if we are adding, the unit must be same. So this diffusion flux will also have the same unit. The second thing what you can you can get idea from your mass balance also. We learned about the mass balance equation, right? That mass balance equation has how the mass is changing with the time, right? So it was kg per second, but flux is per area also. So that's how this will be. So this flux is derived from your mass rate only, but we are dividing it with the area, so that's why this is the flux. So this will again be kg per meter square and multiply by second. So this is how B answer is the right one. Okay, at equilibrium, no molecular motion, no net flux, concentration must be uniform, dynamic exchange continues. Little tricky one. One option that you can neglect is the C1, because C1 is talking about the concentration, and the equilibrium we should talk about the chemical potential, right? So this one is not the right one. Dynamic exchange continue. In the equilibrium, as we already have discussed, that net flux will be equal to 0. So if net flux is equal to 0, it means you will not have the dynamic exchange, that will not be continued. So this is also not the right answer. Then coming to no net flux. As I told you, net flux will be 0. So this one is the right one. No molecular motion. What should be? A should be the right one or not? B1 is the right. Sorry, I think I have given the wrong marking. No, I have given the wrong marking. Dynamic exchange continue. No, this is not the right one. So there should be B answer is the right one. And if we are talking about this A, no molecular motion, so it should be the right one. So according to me, this should be A and B, but I will clear this because I don't know, this is by mistake or there may be some chemistry that right now I don't have in my mind. So I will clear this, but I think that answer should be A and B. Okay, but I will clear this because I'm not trying to make any sense with the D. Anyway, which are true? Diffusion always occur if non-equilibrium exists. Bulk motion can exist without diffusion. Diffusion can exist without bulk motion. Flux is always zero at equilibrium. Okay, so bulk motion can exist without diffusion. Diffusion can exist without bulk motion. This is little trickier, but you can think which one is the subset of which one. So see, A1 is the right one. Whenever there is a non-equilibrium condition, that means we have difference in the chemical potential, and if we do have difference in the chemical potential, then there will always be the diffusion. A is the right answer. Okay, flux is always zero at equilibrium, that you have to see. Then coming to this B and C, diffusion can exist without bulk motion. This one is the right, because we always talked that even if there is no any bulk motion, diffusion will always be there. What about the B? Bulk motion can exist without diffusion. But we already talked that in any condition there will be diffusion. Either there is a bulk motion or not. So four of these options are the right one. There will be the diffusion when there is no any equilibrium condition we have. Then bulk motion can exist without diffusion. There are very rare case about this, but yeah, there may be bulk motion without diffusion. Diffusion can exist without bulk motion. We already have say yes. And diffusion, sorry, flux is always zero at equilibrium. Yeah, we already have learned this. So four of these answers are correct, and maybe you are little confused about this B1. Bulk motion can exist without diffusion. Yeah, this is possible when we have chemical potential is equal in that condition. Okay. Again, we have the equation that is showing you the flux, and again you have to tell me if this term, the first term, is more than Ja, then diffusion can be ignored completely. If v rho a is equal to 0, only diffusion contributes. Diffusion is always 0 when bulk flow exists. Diffusion exists unless equilibrium is reached. So see, for the first term, where we are saying that if we have advection is more than the diffusion, diffusion can be ignored completely. No, we can't ignore it completely, because there will always some value will be for the diffusion. So we can ignore this, but if we are saying that we can ignore it completely, so we are making it zero, we can't make it zero. Okay. The second is, if we have the first term advection is 0, then only diffusion contribute. Yeah, it is right. Diffusion is always 0 when bulk flow exists. No, diffusion can't be 0. Diffusion we can ignore, but we can't say that this is 0. So C is also the right answer. Sorry, wrong answer. Diffusion exists unless equilibrium is reached. Yeah, this one is the right one. So based on that, B and D are the right answer. Okay. So we have four compartment in the environment: river, sediment, unsaturated soil, deep stratified lake bottom. And I have given the numbering 1, 2, 3, 4. And you have to tell me which dominating type of mass transfer. So coming to the river, in the river, more than diffusion, there is advection. Okay. So yeah, this one is correct. For sediment, diffusion is more dominant than advection. This is also right. Coming to the unsaturated soil, diffusion is dominating over advection. This is also right. Deep stratified lake bottom, and this is saying that always well mixed. No, this is not a well mixed. If we are saying it that it is stratified, then it means it is not mixing to the each other. That's why it is making the layers. It is making the layers in the lake. So if there is no any like, if there are layers in the lake, it means it is very difficult to uh, for this mass transfer between these layers. That can only happen when there will be change in the season. Okay, or this stratification will be breakdown. This stratification will always be in tropical countries, but that stratification will be breakdown in temperate region, where there will be change in or shift in the temperature. But because in tropical area there is always the same temperature, then this stratification will not break down, and that's how there is no any well mixing. But in temperate, whenever there is a change in the season, your surface water of the lake will have, let's say, low temperature in the winter, and then in the summer it will have high. So there will be some kind of mixing. Okay, but if it is a stratified, then there is a no well mixing. So D answer is not the right one. So A, B, C. Which statements are correct? Lake are always diffusion dominating. Wind can induce advection in upper layer. Deep lakes may have stratified regions. Entire lake always well mixed. Lakes are always diffusion dominating. Is it? Lakes doesn't have that velocity or that flow. Is it? So you can say that this is right. Then wind can, but it is always. Then you have to think a little bit about this. Wind can induce advection in upper layer. This is true. Deep lakes may have stratified region. This is again true, because whenever we will have deep lake, then based on the temperature and density within the lake, there may be some layers. This is true. Entire lake always well mixed? No, this is not always well mixed. There may be some layers that we may find in the lake, and that layers are not mixing with each other. So B and C are the right answer, because lakes are always diffusion dominating. This is not the right. If you are saying that lakes are generally diffusion dominated, then you can say, okay, yeah. But in the B option, if it is saying that wind can induce advection, it means it is not always diffusion dominated, right? So lakes may also have that advection term. So B and C are the right one, but not A and D. Okay. Velocity, the density, and uh, the diffusion flux is given, and you need to tell me which one is dominating. Diffusion is dominating, advection is dominating, both are equal, or you can't decide which term is dominating. So your advection is V multiplied by rho, and your diffusion flux is J. So this is 10 raised to power minus 5 multiplied by 1, and this is 10 raised to power minus 9. It means 10 raised to power minus 5 is more than 10 raised to power minus 9. So which term is dominating? Which type of mass transfer it will have? Mass transfer will be due to advection, right? Because the diffusion term is 10 raised to power minus 9. Or you can also calculate that Packlet number also. And what you will learn is that 10 raised to power minus 5 is more than 10 raised to power minus 9. It means your advection is more as comparison to your diffusion, and so advection will dominate. So the answer should be B. Okay. If we are having the groundwater transport, velocity is comparable to river flow. Both diffusion and advection are important. Diffusion negligible, flow driven by pressure gradient. In river, the velocity is very high as comparison to the groundwater, so we can't say that velocity is comparable. This one is the wrong one. But diffusion and advection are important. Yes, we learnt about this. Diffusion negligible. I can't say that diffusion is negligible. It is also important term. We can't neglect it. Flow driven by pressure gradient. No, this is driven by hydraulic gradient. So this is also not the right one. Sorry, pressure gradient should not be the right answer, but we do not have much pressure thing in groundwater. But if there is any some pressure thing, then obviously, as I told you, we have driving force. That driving force is directly proportional to your concentration, any type of gradient, and then any type of resistance. So that gradient can be due to concentration, maybe due to pressure, maybe due to uh, voltage difference, something. So this is so in case there is any pressure gradient, no doubt in the groundwater we do not have that pressure gradient, but we are extracting it water also. So in that case you can also consider there may be pressure gradient in the bottom, as the wall, whenever we are having the well, and uh, have you learnt about this Cartesian well? So what happen is, we have Cartesian well. So this is, let's say, your groundwater here, and this is your surface. So it is something that if you are having the well here, then water will be on the surface. This is just because there are some pressure that is maintained, and that pressure is giving me water up to the surface, not here or not here. So it means that your groundwater also have some pressure gradient that can drive the mass transfer. We already have learnt about this transport of volatile chemical, but in a different way. So I'm skipping this right now. Sediment, we already have learned. This one is, I just wanted to have new question. Okay, Packlet number. Can you calculate Packlet number if the velocity, the thickness, and diffusion coefficient is given? I gave you one formula to calculate the Packlet number. What was it? So there is the formula. Let me tell you. Yeah. So the formula for the Packlet number is velocity multiplied by thickness divided by your diffusion coefficient. And if it is more than one, yeah, obviously, then the advection will terminate. Okay, this is, we are now moving to the mass transfer coefficient. So diffusion becomes zero when velocity is equal to zero, gradient is equal to zero, concentration is equal to zero, pressure is equal to constant. In the diffusion, velocity doesn't matter. Gradient, what type of gradient we are talking about? This gradient, so mostly we are saying that this dc upon dx is the kind of gradient that we have, right? And the concentration, obviously in fixed law we are having this concentration, but in different condition what we can have is the chemical potential, and pressure doesn't matter. So gradient will be zero. concentration, actually this is very confusing sometime, because sometime we are referring to the concentration and sometime we are referring to the chemical potential. So it becomes difficult, what kind of things you are referring to. And the important thing that you needed to note down, that this is the boundary condition reasoning. So in the boundary condition, so this was something like, so this is your boundary and these are your, let's say this is your water and then this is your air. Okay, so here, whenever there is some chemical is moving from here to here to here, then this is not the concentration. This in these boundary condition, we mostly talk about the chemical potential, but we do not talk about the concentration, because concentration will always be different, because we are talking about different phase. So that's how C answer can't be the right one. So that's why we are relying on the B answer. So you have to see in what terms we are asking the question. This is same, little same like the previous questions that I already asked. Stratified means uniform mixing. No, stratified means no mixing between the layer. Stratification reduce vertical transport. Yeah, this is right. Wind destroys stratification always. Uh, Wind can destroy the upper one, the upper layer, but if wind is going to the down layer also, then it can destroy the certification, but most of the time the wind will reduce just upper layer of the lake. Certification eliminate diffusion. Diffusion will always be there. Stratification can't eliminate the diffusion, right? So the B answer is the right one. Total flux, I think you can calculate easily using your two terms that you have, diffusion and advection term. Right now, I'm skipping these things so that I can move to the important that I want to show you. Yeah. Yeah, this is a different topic that we are moving. In interfacial mass transfer, the dominant resistance occur where the mostly resistance will occur in the well mixed bulk, at the solid interface only, in the thin concentration boundary layer, uniformly across the entire fluid. Dominant resistance will always be occur in the boundary layer. As I told you, this is your water, this is your gas. So whenever there is a mass transfer from here to here, these so this is very thin boundary layer that we have. So this is the place where we will have the high resistance, right? So that's why, not A. Why there is a? We are talking about interfacial mass transfer, so we do not have well mixed bulk. The question is just, the question is here, the dominant resistance will be where. So that's how C answer is the right one. The resistance will always be higher in the boundary layer, where there is a boundary between two phase. And so again I'm drawing this, so this is boundary, let's say, and this boundary is not just one line, there may be some thickness of the boundary. So this is the thickness we talked about, this L, right? More the thickness we will have of this boundary, more resistance we will have. Okay, and it is very till now it is said that we are not uh, practically we are not able to calculate this, the thickness of the boundary. So we are just having equations and we are ideally or theoretically calculating it, but we are not able to calculate this thickness. But this is very important to calculate the resistance and to calculate the mass transfer. And so C answer is the right one. uh, Increasing flow velocity reduce mass transfer resistance. If we will have high flow velocity, that will reduce mass transfer resistance. This is right. If the velocity will be higher, the resistance will be lower. High velocity increase diffusion coefficient. This is wrong, because diffusion coefficient is not dependent on the velocity, right? So C answer is the right one. This we already have learned. This right now I'm skipping. Yeah, I just wanted to give you some brief about. Let me. Yeah, this one was important part that I wanted to show you, how we can calculate the resistance. I would suggest you to please see this one, how we are deriving the resistance whenever the contaminant is moving from water to gas. I think this is the topic that I should cover in next week, because this is the important one, and how it has been derived. So I think I will try to take it in the next week. Right now I need to go because I have a match I need to play. And yeah, we will meet next week. If you have any query, you can anytime send me an email. I will try to give you the answer as soon as possible. And whenever you have any suggestion, you can tell me. And yeah, thank you, Lakshmi. So, okay, bye.